Hello and welcome to Section 7, where we'll be discussing the origin of our solar system. And for our picture this time, we're looking at the picture of the Great Orion Nebula, where we're going to see regions of gases, dust floating around, and regions of star formation. We all know the drill at this point in the course, so let's go ahead and answer a question. Was it ever possible, or even currently possible, for Jupiter to become a star? Go ahead and pause, think of your answer, come right back. And the answer is no. Jupiter just isn't massive enough. What we can say is that Jupiter is close. Like, say, its composition is too different. This is incorrect. Jupiter has the right composition to be a star. It just doesn't have enough mass to put that material together and start fusing it. And that's our definition for a star, taking two protons and fusing them into heavier and heavier elements. So in this section, we're going to discuss the origins of our solar system, and we're going to apply a physics concept of angular momentum to convey what's going on. And with that angular momentum, we'll figure out some rudimentary ideas of how the planets formed and what's the composition of those planets throughout the solar system. And once we have an idea of our solar system, well, we start talking about exoplanets or extrasolar planets. What happens to the planets? Where do they form, and how do we find them outside of our solar system? Let's put our solar system in scale by looking at these diagrams here. We'll start at the Sun at the center and go out. Mercury, Venus, Earth, Mars. Ceres is a dwarf planet that exists all the way in the asteroid belt. And once you get past that, we can see Jupiter. And of course, we need to zoom out a bit to see the rest of the solar system. So take Jupiter's orbit, this big circle in this top picture, and shrink it down. So in this ring here in this bottom picture, that's going to be Jupiter's orbit. And we'll keep going. Saturn, Uranus, Neptune, and then we'll see more dwarf planets, Pluto's and Eris, out in the Kuiper belt. And what we're going to ask ourselves is, well, what's with this distribution of matter? Why do the planets line up this way? And are there any patterns that we see in the planets? What we know now about the universe is that our solar system is just one of many planetary systems out there. So if we have a model or any theories that explain the origin of our star and our planetary systems, it has to be applicable to all the other systems. We need to be able to explain our planets, moons, asteroids. Think about those asteroid belts and the Kuiper belt. Any model we have needs to try and explain that. The predominant hypothesis that we're going to discuss is what's called the Nebular Hypothesis. Now, its origins dates back to around the 18th, 19th century, early 19th century, and it was independently proposed by the scientist Immanuel Kant and the mathematician Pierre-Simon Laplace. And it goes off this idea of the nebular or cloud. So here we're looking at a nebulous, and you see all the dust clouds springing out here, and due to gravitational forces, there's going to be material falling in, coalescing. In essence, this nebular hypothesis says that a young star will be surrounded by this gas and dust. The star will be the central figure of this a region of space, and everything else about the solar system will form around that initial star. We'll dub what's going to be called a protostar eventually. So here's that nebular hypothesis in one big diagram capturing all the main features. You start with a nebulous cloud that will collapse down to a protostar. Around that star there will be these accretion disks, and in these accretion disks the rings will start coalescing, and as these rings coalesce, the planets will finally form. So let's go through this in a little bit more detail, step by step now. We see tons of these pictures, these beautiful images of nebulae throughout the galaxies and the universe. And these nebulae are just collections of gas clouds. You'll see these star-forming regions inside them. Now, once you have a gas cloud, we're going to simplify our models a little bit and make them nice, perfectly spherical. Every little bit, there will be regions of a slightly higher concentration material. Well, that higher concentration, that higher density, corresponds to a greater gravitational force. So just due to gravity, this cloud starts to collapse in on itself. The solar nebula starts to compress down. Eventually, that cloud will have collapsed enough to create what's called the protostar. Basically, this is a hot ball of gas. You could think of this as a big Jupiter. It's not quite fusing yet. It doesn't have enough mass or density, but that protostar will eventually get there. The material will collapse down enough, create enough pressure, enough temperature in there to turn into an actual star. While that's simultaneously happening, the nebula itself will have begun to flatten and turn into, instead of a big sphere of gas and dust, it will collapse down into this ring that's nice and flat. In the process of falling down, collapsing into this accretion disk, the material will have converted potential energy, gravitational energy, into kinetic energy. And so it'll be rotating faster and faster. And we'll find that the mass around the star now, there'll be a higher concentration. The density will be greater here. And as you get out, there'll be less and less material. And it will be slightly cooler, is what we'll find later on in this section. Eventually, from that accretion disk, the rings will start to coalesce. And it's just due to the different speeds that things are rotating at. They'll start to distribute out, making these nice rings. And once you have rings of material, you can start having your rings collecting into planetesimals, eventually into planets. All right. Each ring here you can think of being defined by the different rotational velocity around that star or protostar. Wait enough time, have enough patience, and all the material in a given ring will start to smack together, globbing together, forming the planets that we see. I've already said this, but let's go ahead and define it properly. Those protostars are large, hot balls of gas, and they are not a star yet. In order to be a star, you must be going under nuclear fusion in your core. Here we see some pictures. If we look into the protoplanetary disk in the Orion Nebula, we're looking on this edge on. And in this one, you can start to see that star, that protostar is starting to get hot enough. It's glowing from just how much thermal energy is there. Well, where'd that come from? Gravitational energy. Remember, these protostars started off as a big, massive nebula that is collapsed down into the protostar. So all of that gravitational energy, when it compressed down into the center of this protostar now, that gravitational energy, it had to go somewhere. Well, it was converted into thermal energy, radiating, heating up that star. Once enough material has collapsed down, it has started rotating around, spinning around fast enough, and has converted enough gravitational energy into thermal energy, and also importantly, pressure in the core of the protostar. That is when fusion can begin, and it turns into an actual star. The remainder of the material from the nebulous that doesn't become the protostar falls into what we call the protoplanetary disk. This is where the protoplanets, the pre-planets, are going to come out of. Emphasis here. Right there, it would fall into the sun. It just becomes part of the sun's mass. Obviously, the sun's going to be the densest, most massive thing in our solar system because it formed at the center of this nebulous. Everything else, the planets, the moons, the asteroids, all of that has to be formed out of this remaining material. And now we're going to start talking about this property of angular momentum and explain why the matter gets distributed this way and what principles of physics dictates what's going on here.